Okay, we finally defined continuous functions, which was the setting for which was what topological spaces are all about. And we motivate this definition by proving a theorem which tells you what it is in a special case. Okay, so suppose we have x, y topological spaces. And f maps x to y. There's a function. So then the definition, so given this data, the definition is f is continuous if for all v in y open, f inverse of v, if this is in x, is open. Okay, now you can see why we made that much of a fuss about inverse images, because the definition of continuity is based on this. Okay, so inverse image of union of sets will be union of inverse images of sets, etc., etc. We'll be using these a lot. Okay, so what motivates this definition? We can take as a basic example, and I'll take a sub-example. So depending on your background, you can focus on one or the other. So if we have x with dx and y with dy, metric spaces, and f mapping x to y. So then this will be the usual definition here, but if the usual definition is not familiar with to you, you can just take x equals y equals r, and this is just basic analysis, and dx of 2 points xy is also the dy of xy, which is just the absolute value of x minus y. Okay, and so we are going to write down so in this case, if I write down x belongs to the ball of radius, ball around a of radius r, that is equivalent to mod of x minus a is less than r. Okay, and this r will be epsilon and delta, and we'll get the usual definitions of continuity from the following theorem. Okay, so f is continuous, and this means in the topological sense, if and only if, and let me call this analysis continuity for just temporarily. Okay, so analysis continuity is if and only if, let me say for all x in the domain, x in x, for all epsilon greater than 0, so analysis continuity is pointwise, so I put it here. Analysis continuity says for all x in x, for all epsilon greater than 0, there exists delta greater than 0, such that, well, I'll write it out not in terms of balls, but in terms of distance. Distance in x between, or let me put for all x naught in x and x naught is less than delta, implies the distance in y of f of x with f of x naught is less than epsilon. Okay, so since distance is difference in absolute values in r, this is just the very familiar definition of continuity in analysis. I will assume that that definition is familiar to you. Okay, so this is analytical continuity, and so this is equivalent. So remark, so analytic continuity so this is equivalent, or so let me not write that here, let's just look at this part. So this part is equivalent to saying that if I look at the ball of radius around x0, if I look at the ball around the point x0 of radius delta and look at its image, it's contained in the ball of radius around f of x0 of radius epsilon. And you can write this in terms of inverse images too. So this is equivalent to this. Okay, so we'll use this in a slightly more convenient way. So proof. So let's assume f is continuous. so when we assume f is continuous, it means inverse images of open set is open. Okay, so fix x naught. We want to prove analytic continuity. Okay, and then we let epsilon greater than 0 be given. And then it's time for a picture. So we have here x, and here we have y, and we have x0, and we have f of x0. And the epsilon being given is a number, but we want to think of it as a ball of radius epsilon being given. This guy, this ball being given here. Okay. And what we want to find is something which is small enough, which goes into this. It may wiggle and so on, but it goes into this. Okay, so that's what the picture is. Okay, so what we know is we have to take an open set and look at its inverse image. But of course, we know that open balls are open. Okay, so by the continuity, we look at f inverse of the ball around f of x0 of y, not y. Y is f of x0, but let's write it of radius epsilon. So this is open. So this is open. Okay. And what we know is x, of course, belongs to f inverse of ball around f of x0 of epsilon. Okay. So by definition of the metric topology, what do we know? Well, we know the metric topology has basis, which is balls. Okay, so there exists delta greater than 0 such that so a priori it need not be a ball around x0. There exists, let me call that delta prime greater than 0, and some other point x prime in x such that if we look at the ball of radius around x prime of radius delta prime, so x belongs to this ball, okay, and this ball is contained in the set f inverse of ball of radius f of x0 and epsilon. Okay, so this has got slightly messed up, so I mean it's called correct, but so let's cleanly note what we have here again in a picture. So we have a space x, we have another space y, and we have continuity, and continuity is saying inverse image of open set is open. So we have here x0, and we have f of x0, and our epsilon gave us an open ball of radius epsilon around this. So its inverse image is some set. We know that's open because the inverse image of open sets is open. Okay. So now given a point here inside x0, we have effectively proved this once before, but now we have not stated it, so let's go with the definitions. So what we have to do is we are given a point x0, it's inside this open set. So that means it's contained in a basic open set, and the basic open sets are balls, but so far we don't know that they're actually centered around x0. So what we have instead is this orange ball centered around maybe another point, which was a red point here, and this red point here is x prime. Okay, so we have x prime, or maybe I'll call it x0 prime here as well, because it's a modification of x0. Okay, but for the analytic definition, I wanted a ball centered around x. Okay, but that we can find just as we did previously. Let's zoom into this picture a little bit. So zoomed in, there is a ball around a point. There's an orange ball centered around the point red, which was x0 prime, and x0 sits somewhere here. Again, because x0 is in this ball, we can find a this distance is less than the radius of the ball, which was delta prime. So this is radius delta prime, and so we can find, using the triangle inequality, a smaller ball contained here. Okay, and what is the size of the smaller ball? This is exactly what we did when we showed intersection. We showed open balls as a basis. But at that time we didn't state what this theorem is, which is exactly talking about neighborhood basis. So let's actually prove it properly here. So as x0 belongs to this ball around x0 prime of delta prime, distance between x0 is less than delta prime. Okay, so what is the size of this ball? Well, so there is some room. Okay, so that is, so let delta is delta prime minus d of x0. Okay, last time I took minimum of two quantities, meaning when we were looking at metric being a basis, and said less than that. So this time, for definiteness, for a change, we'll take this difference as delta is prime minus d of x. This is not readable. There's no x here. This is x0 prime. So we look at the distance between these two, which is symmetric. So note that this is just less than delta prime minus d of x0. And now our claim is that the ball of around the point x0 of delta is contained in ball around x0 prime of delta prime, which, remember, is contained in F inverse of the ball of so I'm putting it in parentheses because our claim is this part, is what we are proving, but we have already observed, the reason we are bothering to prove this is if I look at ball of radius f of x0 of epsilon. Okay, so proof of claim is, let proof of claim is triangle inequality as before. If x belongs to ball of x0 of delta, then distance between x and x0 is less than delta. That's the definition. Therefore, distance between x and x0 prime, okay, by triangle inequality, this is less than or equal to distance between x0, and so there are two sides to the triangle. I am looking at distance between x0, which is small, and distance between x0 and x0 prime. Okay, and this distance is less than, so this is less, so this distance is distance between x0. I have not changed anything, but you note that this distance is less, the second distance is less than delta prime minus distance between x0 prime. Okay, oh sorry, this is x0 prime. We have left the second quantity alone. Yeah, so let's check this again. The distance between x and x0 prime is what you want to show that it is in this ball. Okay, so that is telling you it's less than or equal to distance between x and x0. I'm sorry. So the first term is x and x0 plus delta prime minus distance between x0 and x0 prime. Let me correct myself. This was somewhat blind calculations. Let's calculate with a little intelligence. So here we are. We want to know this. Okay, so let's note down what we actually have. This distance between x and x0, because of the definition, distance is, so this is less than delta plus distance between x0 and x0 prime. Okay, and what we know is that delta is less than delta prime minus distance between x0 plus this, and that's this first term is these two, and the distance between x0 prime and x0 prime, which is equal to delta prime. Okay, so that's the claim. That is, x belongs to the distance between ball around x0 prime of delta prime. Okay, so thus distance between x and x0 is less than delta, implies, indeed this part is equivalent to, x belongs to the distance the ball, so I can as well say is of radius, equivalent to ball around x0 of radius delta, which is contained in, so this is equivalent to this, yeah. Now this is contained in F inverse, since that is the statement here, let me write it this way. So this implies something. So this ball is contained in F inverse of ball around f of x0 of epsilon. So that means, which implies f of x is contained in ball in f0, f of x0 of radius epsilon, which implies that distance, in fact this part is again equivalent, of f of x0 is less than epsilon. So we've got exactly the analysis definition from the topology definition. Okay, we had to do a little bit of work because our basic open sets, we have defined them to be balls around points and not necessarily balls about the chosen point. So we had to pass from the chosen point by a little bit of geometry to the arbitrary point around which we took a ball. Okay, this leaves us with another side of the result. So what we have seen is the topological definition implies the analytical definition. The converse is a little bit easier. So conversely, let's assume the analytical definition. So conversely, assume analytic continuity, that is, given every point we have for all epsilon, etc., etc. Okay, assume analytic continuity. Okay, then so let V contained in Y be open. So what we have to claim is that F inverse of Y V is open, and almost mechanically let X belong to F inverse of V. Okay, so we know how we can define openness in terms of basis. Okay, so we show that we'll find a basis vector, which is, so here we are, we have V here contained in some bigger space Y, and we have X here, and the inverse image is a set which we want to control, and we have a point little x here in this point. What we know is that it goes in here. Well, it goes to f of x. What we want to what we will show is that there is a basic open set. In this case, it's centered around x, which is contained in x and contained in f inverse of v. And since x is arbitrary, this will show that there is. So we show there is a basic open set. It's a ball, and since we have to show existence, we can be more specific. In fact, it's going to be of this form, b delta fx, which is contained in V, such that x belongs to b delta fx. The second part is obvious. Okay, this will show openness. This shows V open as x is arbitrary, so for any arbitrary point. So now it's quite clear what we have to do, namely, okay, as V is open and f of x belongs to V. I will have to repeat the circus of last time, but this time in V, but we won't repeat it in detail. What we know is that there is a ball with some center which contains V, and f of x belongs to V. There exists a basic open set, ball around some radius epsilon prime at ball centered at some point y, with radius epsilon prime. This is contained in Y such that f of x 0 belongs to this basic open set, and the ball of radius and this ball is contained in V. Okay, so clearly, since we have used it twice, we should have encapsulated this as a lemma. We'll do post facto. For now, we'll say as in the other part. There exists epsilon greater than 0 such that the ball around the point f of x of radius epsilon, this is contained in the ball of radius around y of epsilon prime. Okay, and that in turn is contained in V. Okay, so now that we have this, so we pick delta greater than 0 corresponding to epsilon. Okay, then x prime or something belonging to the ball around x of radius delta implies that f of x prime belongs to the ball around f of x naught of radius epsilon, which is contained in V. So thus ball at around of radius x of delta is contained in f inverse of V as claimed. Okay, well, strictly speaking, I should also mention x belongs to a ball of x radius x of delta. So we have picked, since this is positive delta, x belongs to a ball of any positive radius about itself. This is contained in f inverse of V. So what we see is, given any V, we look at f inverse of V, and we show any point is contained in a basic open set, which is contained in turn in f inverse of V. And so f inverse of V is the union of these basic open sets, and hence is itself open. So a union of open sets is open. Okay, so this proves that if we have so again, to choose the epsilon, we have to adjust the ball a little bit in the domain. So this will justify defining what we mean by neighborhood basis, and seeing that balls around the point are actually a neighborhood basis. But nevertheless, we have proved that if you have analytic continuity is the same as topological continuity. So this justifies both formulating topology in terms of open sets, since continuity could be defined entirely in the terms of these, and the specific definition of continuity. We will say this particular result extends to saying continuous at every point in a topological space is continuous. I mean, by extend, I mean has essentially the same proof shows this. But continuity is a much richer concept. We'll see a lot about it through the rest of the course.